Okay. All right. Okay. Let me see. So it's recording right now, and I need to share the screen. All right. Okay. All right. So let's continue with our advanced mathematics. In this video, I want to continue with the second principle of mathematical induction, and I'm going to use that principle, the strong one, to prove one of the most important theorem in mathematics, which is the fundamental theorem in arithmetic. And I don't know if you guys still remember that theorem. So I'm going to do a quick recall what fundamental theorem of arithmetic first. Okay. So let's start with that. I can use the red pen. All right. So fundamental theorem of arithmetic. And this theorem said that for every integer that greater than or equal to 2, okay, that's greater than or equal to 2, it can be written as the product of all the prime. Okay, it can be written as a product of all the prime. So n can be written as p1 times p2 times pr. Okay, or it can be written as the product of all the power of the prime. It can be written as the product of all the distinct power of the prime, or it can be written as the product of all the power of all distinct prime. So it could be p1 r1 times p2 r2 times p. I think I should use another letter. It should be alpha 1, alpha 2, alpha np, alpha npn. Okay. Right. So p1, p2, pn over here is this. It is distinct prime. Okay. And p1, p2 times pr over here is not distinct. Okay. It could be the same. For example, p1, p2 could be 2, or p3 and p4 could be 3, something like that. But over here, p1, p2, and pn must be distinct prime. Okay. For alpha 1, alpha 2, and alpha n, it could be the same. For example, alpha 1, alpha 2 could be the third power or the second power. It doesn't matter. So that is basically what a fundamental theorem of arithmetic is. Okay. So I can give you a quick example here. For example, like 16, right? 16, I can write it as 2 times 2 times 2 times 2, right? Or you can write it as 2 to the third power. Okay. Let me use another number. That's harder. Let me use 100. So 100 is what? 100 is 2 times 50 divided by 2 is 25. Be 5 times 5, right? Right, 5 times 5, right? So you see 2 and 2 is repeated, but it also can be written as 2 second power times 5 to the second power. You see that 2 and 5 where they are distinct prime. Okay, they are distinct prime. All right. So basically, that's what a fundamental theorem of arithmetic is. I want to prove. I want to use the second induction, the strong one, to prove this. And the problem is when they the question they ask you to prove fundamental theorem of arithmetic using second induction, they never ask you like this. They never say that use second principle of induction to prove a fundamental theorem of arithmetic, but the question it is always like this. It say that use a strong induction to prove that every natural number that's greater than or equal to 2, every natural number that's greater than or equal to 2 is either prime or the product of prime number. So if you read the question here, it is the same as they asking you to prove fundamental theorem of arithmetic. Okay, but they never say that use a strong induction to prove every integer is greater than or equal to 2. It can be read as the product of a prime number as the product of the power of distinct prime. They never say like that. Okay, they just say that use strong induction to prove that every natural number is greater than or equal to is either a prime or the product of a prime number. Okay, so I mean, if you read the question, it's kind of just like this part only. Okay, not this part. They don't want you to prove this part. Okay, they don't want you to prove this part. They just want you to prove this. It means that n over here can be written as the p1 times p2 times pr. Okay, and p1, p2, pr it can be repeated. Okay, it doesn't have to be distinct. You go over here, they just say that it's as a product of prime number. They didn't say it as a product of distinct prime number. Okay, so how are we gonna do this? So in order to use to prove this, and you have to use strong induction. I don't know you guys do remember what strong induction is. Like in the previous video, I already talked about strong induction, and I say that if PM plus 1, PM plus 2, the statement, right, and what, and PM is true, right? PM is true, and if PI is also true for all the statement for all the and PI is also true for I between M and K. Okay, that implies PK plus 1 is true. Then PM plus 1, PM plus 2, PM plus 3, PM plus 4 is also true. So that is one of the version. That's one of the way of writing a strong induction. Another way of writing a strong induction is this: if P is true for the some integer n0, okay, and if K greater than n0, okay, if K greater than n0 and P is also true for all the value between n0 and K. Okay, then it is also true for the value K. Okay, then we can say that P is true for all the integer when n is greater than n0. Okay, so it's just another way of writing second principle of mathematics. Okay, second principle of mathematical induction. Okay, so let's get started. I think I'm going to use the second version of writing to prove it. I mean, I can use the first one, but I think the second one is easier. So so first of all, we need to set the hypothesis, right? And over here we want is the ordered natural number that's greater than or equal to 2. So we have to check for the n0 equal 2, right? N0 equal 2, and 2 is a prime. So 2 is a prime already. So this is true, right? Because a prime number can be written as a product of a prime number. This makes sense. Okay. Now we start with our hypothesis, and if k, now let k greater than 2. Okay. And we assume that the statement, let me fix this a little bit here. Okay. We assume that the statement is true for all positive integer it's true for all positive integer between 2 and k. Okay, that positive integer here I can write it as the L number. Okay. So it means what? It means that for all the positive integer here between 2 and k, it can be written as the prime or the product of prime number. That's what I mean. Okay, that's what I mean. So it means that all integer between 2 and k can be written as a product of prime number or prime itself. Okay, that's what it means. Okay, so that is our hypothesis. That's our hypothesis. Okay. Then what next? What is the next step? Our next step is we need to show that oh, this is okay. Okay, we need to show that this is also true for k. It's also true for number k. Okay, so how are we going to do that? We assume that between 2 and k, not including k, it can be written as a prime, as the product of prime. But we need to show this is true for k. Okay, so it is also true with k. Okay, it's also true with k number. All right, so how are we going to do that? I mean, if k is a prime number, then it's trivial, right? If k is a prime number, then you can write it as a prime number because, for example, 2 you can write it as 2 multiplied by 1. Okay, but what if k is not a prime number? Okay, for example, I say if it is not a prime number, you can k is a composite, right? K is a composite. It means that you can write it k as k equal to a product of A and B. Okay. And if you write case as a product between A and B, it means what? It means that A and B, mean that A and B must less than K, right? But greater than equal to 2. Okay. Right. For example, like you 6 equal to 2 and 3, and 2 and 3 of course must be less than 6, right? And greater than or equal to 2. Okay. And if A and B is less than K, greater than or equal to 2, we use the hypothesis. Okay, we use the hypothesis. It means what? It means that A and B. It means that A and B is either prime, right, or the product of prime number. Okay. It's either prime or a product of prime number, right? Because we had this as the hypothesis. We say that any number between 2 and K, okay, not including K, can be written as a prime itself or a product of all prime number. In this case, I say that now we deduce that A and B is less than 2 and K. Then of course A and B is either prime or the product of all prime number, right? Okay, and so what? Okay, we just successfully show that K can be written as the product of prime number or prime itself, or either prime or the product of prime number, right? So K is a prime number, is prime or a product of prime number. Okay, and if K is a prime or is a product of a prime number, then what? Then we can conclude. Okay, then we can conclude the final statement. We can conclude that every integer greater than 2 is either prime or product, okay, of prime number. Okay, that's it. So I mean, it's not really that bad, but the thing is that when you use the second principle of mathematical induction, you have to be flexible a little bit, okay? Because there are 2 or 3 way of addressing this principle. Last time when I give you the video, I think the second video, in the second video, the way I wrote down the strong induction is a little bit different from this. Okay, but this time I use this way. This time I use a different form. It's not different form. I can say that a different way of addressing second principle of mathematical induction. Okay, so if you go back and you watch the video, the second principle of mathematical induction, and you compare to this one, you will see they're different, but it's very subtle different. It's not really a lot, but the meaning is still the same. Okay, so we successfully prove a part of fundamental theorem of arithmetic. It's not, we're not really proven everything. We're just proven this. Okay, we've proven this. On the rest of the video, I just want to bring up called that is called Russel Paradox. I think this paradox is worth thinking about. It's worth contemplating it. Okay, you can use this paradox to train your mind, to train your brain. I don't know if you guys heard of a Fermi paradox or not. Um, uh, it's not relevant to a Russell paradox, but I mean, when the Fermi paradox is the paradox is say that there exists there's alien civilization in the universe other than the Earth. Okay, but at the same time, they say that if there exists a civilization other than Earth and it's more advanced than ours, then we've been waiting for a very long time, and we have not received any signal from them. Okay, all the visit we heard so far is just a theory of conspiracy, right? And even though that we send a signal to outer space and you go to another galaxy and we send it to another star, and we have not received anything back. So that is the Fermi paradox. And the Russell paradox is totally different. It's just math. But I want to bring it up because it's worth contemplating it. Okay, and the paradox say that if R represent for the set Russell set, if R is a set that is contained on the set, okay, it's the set that contained on the set that does not contain itself. Okay, it's contained a set that does not contain itself. I don't know if you guys already learned set theory, and you guys know that every set contain the empty set and contain itself. Okay, now I say Russell set is the set that does not, is the set that is Russell is the set that the member is a set that does not contain itself. Okay, but the question is this set R here is containing itself or not? Okay, it's containing itself. It's very interesting, guys. It took me like 15 minutes to figure it out, and it's quite a very interesting because it was my first time knowing this also, but it's worth thinking about. Okay, the question is if Russell set is containing itself or not. Okay, just look. This is what an interesting part right here. If Russell set containing itself, okay, if R is containing in R, what is happening? If R is containing in R, if R is containing in R, what is happening? If R is containing in R, if R is containing in R, it means what? It means that R does not belong to this set, right? Because this set over here, this Russell set here contains all the set that is not containing itself. But right now, R is containing in R. It means R does not belong to this set. Oh, interesting, right? And now, if so, this contradiction, right? There's a contradiction right here. And if R does not contain itself, if R does not contain itself, then it means that R is all, because if R does not contain itself, it means R is a member of set R, right? Because R contain, when we hear R contain on the set that is not containing itself. And now R does not contain itself, it means R also belongs to R, right? Oh, look at that. Look at that. Yeah, there's a contradiction everywhere right here. It's everywhere right here. So, I mean, this is quite very interesting right here. I mean, and we think of that, and I was like, oh, how come it's like that, you know? And this paradox over here, it shows us that set theory is inconsistent. And in order to solve this problem, then how are we going to fix it? In order to fix this, we must have uh, a level for all the set. Okay, what I mean over here that the sets must have a hierarchy. Okay, must have a hierarchy because it totally is. You can see over here is contradiction everywhere. Okay, contradiction everywhere here. It's contradict to this and this also. It's, so I mean, it's very interesting. I mean, after I noticed, I was like, oh, wow, it's. I mean, I did some research on set theory, but I mean, I see it. I was like, wow, that's really great. You know, it's really great. And I don't know uh, what we're gonna do with this paradox. We just this paradox will just show us that there's an inconsistent in the set theory. I don't know any other than that. But I mean, if you guys watch a video and you guys found something else, and just let me know. Okay. So I think that's all for the video today. Um, I'm gonna see you next time if I find out something interesting. Okay. Thank you. Bye bye.